The human gaze toward Mars represents an endless yearning for a distant home, a history that can be traced back to the invention of the telescope. In the 17th century, when Galileo Galilei first pointed his telescope toward that crimson orb in the night sky, Mars ceased to be merely a flickering point of light and became a planet waiting to be deciphered. Over the following centuries, as observational technology advanced, some astronomers even identified regular geometric lines on the Martian surface, famously known as the Martian canals. These features sparked the imaginations of countless science fiction writers, who depicted Mars as the abode of an ancient and wise civilization, a world of flowing water and thriving life. Such romantic and mysterious fantasies represented humanity's first and most profound calling toward Mars. However, scientific exploration is always grounded in rigorous data and empirical evidence. This story is long, and perhaps we shall delve deeper in our dreams. Before we begin, do not forget to like and share. By the middle of the 20th century, with the development of aerospace technology, humanity was finally able to send probes to this mysterious red planet. The Mars series from the Soviet Union and the Mariner series from the United States, acting as the earliest interplanetary messengers, unveiled a corner of the true face of Mars. The images they transmitted showed a surface scarred by impact craters and an atmosphere far thinner than that of Earth. These initial findings, while shattering the romantic illusions of canals, ignited deeper scientific questions. Did Mars once harbor life? What secrets are hidden within its geological history? The true breakthrough occurred in the 1970s when the United States launched the Viking program, sending 2 landers and 2 orbiters to Mars. This marked the first human attempt to search directly for signs of life on the Martian surface. Although the experimental results did not explicitly confirm the existence of life, the detailed exploration of the Martian atmosphere, soil composition, and meteorological conditions by the Viking missions laid a solid foundation for more profound subsequent investigations. It led us to realize that Mars is a world full of challenges but not entirely devoid of activity. Entering the new millennium, Martian exploration transitioned into a completely new era. Orbital probes such as Mars Global Surveyor and Mars Odyssey acted as tireless scouts circling above, mapping detailed geological charts and discovering vast evidence of water ice, particularly at the poles and beneath the regolith. These discoveries were undoubtedly revolutionary because water is the essential element for life and provides critical resource leads for future human landings. This was followed by the era of the rovers, allowing humanity to touch Mars at a closer range. In 2004, the Spirit and Opportunity rovers successfully landed, conducting scientific surveys for several years and traveling dozens of kilometers. The countless images and data they returned clearly revealed strong evidence that liquid water once existed on Mars, such as erosion patterns from water flow, hydrated minerals, and sedimentary rock layers. The extraordinary performance of Spirit and Opportunity greatly encouraged scientists to continue exploring the historical habitability of Mars. In 2012, the more advanced Curiosity rover successfully landed in Gale crater. Carrying sophisticated scientific instruments, it aimed to search for past or present habitable environments. Curiosity's findings indicated that certain areas of Gale crater did indeed possess environments suitable for microbial life billions of years ago, featuring liquid water, essential chemical elements, and energy sources. Its discoveries further strengthened our confidence that Mars was once a cradle for life. In 2021, the Perseverance rover landed in Jezero crater, accompanied by a helicopter named Ingenuity, which achieved the first powered flight on another planet. Perseverance's mission is to search more deeply for ancient biosignatures and collect rock and soil samples for a future sample return mission. If these samples can be successfully returned to Earth, they will fundamentally change our understanding of the possibility of life on Mars and may even reveal clues about the origin of life on Earth. It is also worth noting that China has taken a historic step in Martian exploration. In 2021, the Tianwen-1 probe arrived at Mars and released the Zhurong rover, which landed on the southern Utopia Planitia to conduct surveys. The wealth of scientific data obtained marked China's rise in deep space exploration, making it the second nation after the United States to successfully land and operate a rover on Mars. Currently, the international community's enthusiasm for Martian exploration is at an all-time high. In addition to the United States and China, space agencies from the European Space Agency, Japan, India, and other regions are actively advancing their respective missions. The Mars Sample Return Program is considered the top priority of the next decade, representing the first time humanity will bring samples from another planet back to terrestrial laboratories for detailed study, which carries epochal significance. Looking ahead, crewed missions to Mars are no longer an unreachable dream. Organizations including NASA and private enterprises like SpaceX have formulated ambitious plans for human landings. Although faced with immense technical, physiological, and economic challenges, the pace of human progress toward Mars is becoming increasingly clear. We are preparing for that historic moment when the first group of astronauts sets foot on the red planet. That will be another great leap for the human spirit of exploration and the opening chapter of Mars as our next home. The call of the red planet has never been so real and intense. Although the surface of Mars appears desolate and lonely, its hidden mysteries and potential resources are drawing the human gaze and forcing us to consider a critical question: can we survive there? To answer this, we must first understand the Martian environment, which is filled with both challenges and opportunities. One of the most significant environmental features of Mars is its extremely thin atmosphere. The average atmospheric pressure is less than 1% of Earth's, consisting primarily of carbon dioxide. This means that liquid water cannot exist stably on the surface; it would rapidly boil, evaporate, or sublimate. Simultaneously, the thin atmosphere results in extremely low surface temperatures, averaging around -60 degrees Celsius, with massive fluctuations between day and night that can drop below -100 degrees. Such harsh conditions of low temperature and low pressure are immense challenges for humans who rely on Earth's atmosphere. Future settlers will need to rely on sturdy pressurized habitats and advanced life support systems to recycle air, water, and food. However, within the seemingly barren Martian landscape lies the key element for life: water ice. Through surveys by orbital probes and rovers, scientists have confirmed that massive water ice caps exist at the Martian poles, with volumes comparable to glaciers on Earth. Furthermore, water ice is widely present deep underground and within the soil of high-latitude regions. These resources are vital for future Martian colonies. Water can be used for drinking and, through electrolysis, can be split into hydrogen and oxygen. The oxygen can be used for breathing, while the combination of hydrogen and oxygen serves as rocket fuel for returning to Earth or for further deep space exploration. The effective utilization of these local water resources is the key to the success of Martian migration and a prerequisite for self-sufficiency. Despite the hope brought by water, the Martian environment presents two severe threats: dust storms and radiation. Martian dust storms are massive in scale, potentially covering the entire planet for weeks or months. These storms block sunlight, affecting solar power generation, and cause wear on precision instruments or block mechanical components. Future bases must be designed to withstand these storms and develop energy systems independent of sunlight, such as nuclear power. Even more concerning is radiation. Due to the thin atmosphere and the lack of a global magnetic field, high-energy solar particles and cosmic rays can reach the surface directly. This high-energy radiation poses a serious threat to astronaut health, potentially causing cancer, genetic damage, and acute radiation sickness. Therefore, constructing habitats with sufficient shielding is a top priority. This may involve burying habitats underground or using thick local materials like rock or ice as shielding. As for the Martian soil, it presents both a challenge and an opportunity. The soil contains high concentrations of perchlorates, which are toxic to humans and affect plant growth. Before farming can occur, the soil must be treated to remove or neutralize these substances. Yet, Martian soil is also highly versatile, rich in minerals like silicon and iron, which can serve as raw materials for construction. Through three-dimensional printing technology, habitats and laboratories can be built directly using Martian soil, reducing the cost and difficulty of transporting materials from Earth. This strategy, known as in situ resource utilization, is indispensable for long-term settlement. Beyond environmental challenges, crewed missions face severe physiological and psychological hurdles. During long-duration spaceflight, astronauts suffer from the negative effects of microgravity, including muscle atrophy, bone density loss, cardiovascular decline, and vision problems. To combat this, rigorous physical training and pharmaceutical interventions are necessary. Once on Mars, living in confined, isolated bases far from Earth will test psychological health. Feelings of loneliness, depression, and isolation, combined with the immense pressure of the mission, could lead to psychological issues. Therefore, strict screening of psychological resilience and providing continuous support and entertainment during the mission is essential. Due to the vast distance between Earth and Mars, emergency response and medical care become exceptionally complex. Communication delays can last up to 20 minutes, meaning doctors on Earth cannot provide real-time guidance. Thus, future teams must include experienced doctors and be equipped with comprehensive medical facilities, including remote diagnostic technology and automated medical systems. Facing these challenges, scientists and engineers have begun envisioning future Martian base designs. Early bases may be relatively simple, consisting of inflatable habitats, small labs, and basic energy systems. As missions deepen and populations increase, bases will expand. One attractive concept is utilizing natural Martian features like underground caves or lava tubes, which provide natural protection against radiation and micrometeorites. Future bases will rely heavily on local resource utilization, extracting oxygen and water from the atmosphere and soil, which will lay the groundwork for true self-sufficiency. In summary, Martian habitability is not achieved overnight. It requires overcoming natural and physiological barriers through advanced technology and meticulous planning to transform the red planet into a home capable of supporting human life. When we discuss Mars beyond its scientific mysteries, a grander vision takes root: Martian migration. This is no longer just a plot for science fiction but a blueprint being seriously discussed and implemented. But why Mars? What is the driving force behind migrating to this distant red planet? First, it is a strategic choice for the continuation and expansion of human civilization. Earth is our cradle, but it is not a permanent safe harbor. Natural disasters, global pandemics, asteroid impacts, or even human behavior could deal a devastating blow to our ecology. Not putting all of our eggs in one basket and establishing a permanent settlement on another planet can effectively mitigate the risk of a single catastrophe, ensuring the survival of the human race. Mars, as the closest planet with a relatively controllable environment, is the natural choice for a second home. Secondly, Mars holds immense potential for resource development and serves as a strategic outpost for deep space exploration. While our understanding of Martian minerals is not yet exhaustive, it undoubtedly possesses the elements required to build and maintain a colony, such as iron, silicon, and sulfur. In the future, Mars may even reveal rare minerals that are scarce on Earth. More importantly, Mars can serve as a springboard for exploring the deep solar system. Once we establish a self-sufficient base, it becomes an ideal departure point for the asteroid belt, Jupiter, and beyond, greatly reducing the cost and difficulty of deep space exploration. Finally, Martian migration is the sublimation of the human spirit of exploration. From gazing at the stars in ancient times to the age of discovery and the moon landing, challenging the unknown and surpassing limits has always been the eternal driver of human progress. It will inspire global creativity and courage, pushing technology forward at an unprecedented speed and creating a broader living space for future generations. The path to Martian migration will be a phased process. Initially, pioneer missions led by robots will play a crucial role. Before humans arrive, they will use automated technology and local resources to build infrastructure, such as pressurized habitats and power systems. These robotic vanguards will lower the risk and complexity for human astronauts. Following the construction of infrastructure, crewed landings will be a milestone step. These early missions may be short-term stays to test life support and scientific experiments. As experience grows, humanity will establish the first small permanent bases. While initially dependent on Earth for supplies, the goal is to achieve self-sufficiency by growing crops in controlled environments and recycling all resources. The ultimate vision is long-term habitation and population growth. When the base can independently produce food, water, and energy, it can support a larger population, eventually forming a true Martian society with its own economic models, social structures, and culture. Conceiving a future Martian society is a fascinating topic. Establishing effective governance and legal systems will be vital. Given the unique environment, it may require a new set of rules different from any on Earth to adapt to resource constraints. This could be a democratic or semi-democratic polity established by scientists, engineers, and early settlers. The Martian economy will revolve around resource development, space tourism, scientific research, and technological innovation. Unique minerals may be discovered for use on Earth, and the allure of extraterrestrial settlement will give rise to high-end space tourism. Furthermore, innovations born on Mars, such as advanced life support and radiation shielding, will find applications back on Earth. Culturally, Martian residents will develop a unique identity, facing shared challenges and limited resources. Their art, music, and literature will likely carry the spirit of space exploration and frontier pioneering. While distinct from Earth, the shared heritage of humanity will remain the foundation of Martian civilization. Mars will also become a new frontier for education and research, attracting the world's best minds to explore the origin of life and planetary evolution. Finally, if Martian migration is the attempt to survive on another world, planetary engineering is the grand vision of completely transforming a planet to make it more like Earth. While this sounds like myth, it is a future possibility under serious discussion. However, before delving into technical paths, we must examine the philosophical and ethical foundations. Do we have the right to change the natural state of a planet? If unknown microbial life exists in some corner of Mars, would large-scale engineering cause irreversible harm? These are ethical dilemmas that must be considered before any transformation begins. Despite these challenges, the concept of terraforming Mars remains a compelling vision for the future of humanity. The core objective of terraforming is to augment the atmospheric pressure of Mars, raise its ambient temperature, and ultimately restore stable liquid water to its surface. Increasing the atmospheric pressure stands as the primary step in this planetary engineering process. Currently, the Martian atmosphere is too thin to effectively shield against solar radiation or sustain liquid water. One major strategy involves releasing the solid carbon dioxide trapped within the polar ice caps. By employing targeted heating or deploying dark albedo materials to absorb more sunlight, we can induce the sublimation of this dry ice into the atmosphere. Carbon dioxide is a potent greenhouse gas capable of effectively absorbing solar radiation, thereby gradually raising the planet's temperature. Another more controversial proposal involves directing asteroids rich in ammonia or methane to impact Mars. The energy released during such impacts would liberate vast quantities of greenhouse gases, significantly boosting the temperature and atmospheric pressure within a short time frame. Raising the temperature is a critical step that must occur alongside atmospheric enhancement. Beyond increasing greenhouse gas concentrations, scientists have conceived other bold technologies. One such concept involves deploying massive solar reflectors in Martian orbit. These mirrors could focus sunlight onto specific regions of the surface to elevate local temperatures and accelerate the melting and sublimation of water and carbon dioxide ice. A relatively simpler alternative is the darkening of the Martian surface. By spreading dark materials across the ground or cultivating dark microorganisms to absorb more solar radiation, the surface temperature could be increased. Only when the temperature and pressure reach specific thresholds can liquid water exist stably. At that point, the vast reservoirs of water ice within the polar regions will become vital. This meltwater could form rivers, lakes, and perhaps even small seas. However, the total water inventory on Mars may not suffice to create oceans as vast as those on Earth. Therefore, some radical visions include harvesting water from comets or icy asteroids in the outer solar system and directing them toward Mars. This would be a project of immense scale and technical difficulty, but theoretically, it could provide the necessary hydration for the planet. However, merely possessing an atmosphere and liquid water is insufficient to make Mars a second Earth. The absence of a global magnetic field is the fundamental cause of its environmental vulnerability. Without the protection of a magnetosphere, the solar wind would continuously strip away the atmosphere, rendering the terraforming efforts futile. Consequently, establishing or restoring a Martian magnetic field is the most challenging task in planetary engineering. Currently, scientists have proposed two primary concepts. The first involves generating an artificial magnetic field, which might entail deploying large superconducting coils in orbit to create a powerful magnetic field through electric currents, thereby deflecting the solar wind. This technology requires immense energy and represents an extreme engineering hurdle. The second, more speculative vision is to reactivate the liquid iron core of Mars to regenerate a natural magnetic field. This might involve injecting energy into the planetary core or increasing its internal convection. However, our current understanding of and ability to intervene in planetary cores is far from reaching such a level. Once the Martian environment becomes sufficiently mild, with liquid water and a denser atmosphere, the introduction of vegetation and the establishment of an ecosystem will be the next step. This requires a rigorous screening of terrestrial plant species to identify resilient flora capable of surviving in the early stages of a modified Martian environment. These plants would not only release oxygen through photosynthesis but also stabilize the soil and improve its structure through their root systems. Before plants are introduced, microorganisms will serve as pioneers. Extremophiles could survive in the initial harsh conditions and gradually alter the chemical composition of the Martian soil, creating conditions suitable for higher plant life. Establishing a Martian ecosystem will be an incredibly long and complex process, potentially spanning hundreds or thousands of years, representing the ultimate test of human patience and perseverance. Planetary engineering, the most ambitious modification project in human history, is significant not only for creating a new home but also for advancing our understanding of planetary science, environmental engineering, and life sciences to unprecedented heights. Simultaneously, it reminds us that transforming a world requires collective wisdom, courage, and a long-term perspective, as well as a profound respect for life and nature. As the dreams of Martian migration and planetary engineering gradually become reality, a completely new Martian civilization will bloom in the cosmos. The birth of this civilization is not just an expansion of human living space but will also have a profound backfeeding effect on terrestrial civilization, eventually outlining the future path for humanity beyond Earth. This feedback will be multifaceted. First, the immense challenges of Martian exploration will catalyze original scientific discoveries and technological breakthroughs. To survive in extreme environments, humans must develop more efficient energy systems, advanced life support technologies, radiation-resistant materials, and more intelligent autonomous robotics. These frontier technologies born on Mars can be applied back to Earth to solve issues like energy shortages, environmental pollution, and healthcare, driving the rapid development of terrestrial technology. For instance, closed-loop ecological agriculture designed for Mars could help Earth achieve more sustainable food production, while radiation protection techniques could be utilized in medical safety or nuclear energy applications. Second, as Earth's resources become increasingly depleted, Mars may provide new sources of materials. While the specific distribution of Martian mineral resources is not yet fully understood, the discovery of rare elements or large-scale common minerals would greatly alleviate resource pressures on Earth. Mars might even become a massive celestial factory, utilizing its unique low-gravity environment and abundant solar energy to manufacture advanced materials that are difficult to produce on Earth. On a deeper level, this feedback is reflected in the expansion of the human spirit. Overcoming the severe challenges of Mars will significantly boost human confidence and our ability to face future obstacles. This collective sense of achievement will inspire society to break through limitations and attempt feats that once seemed impossible. Mars will become a symbol of wisdom and courage, inspiring generations to pursue excellence. However, the evolution of a Martian civilization will not be without friction. It will face complex relationships with Earth and its own internal challenges. What kind of connection and independence will exist between Martian and terrestrial civilizations? Initially, Martian settlements will undoubtedly rely heavily on Earth for supplies and technical support. But as the population grows and self-sufficiency increases, Martian residents may develop a distinct culture and identity, perhaps even seeking political autonomy. This process of separation and integration will be an unprecedented social experiment requiring wisdom from both sides. The unique Martian environment will shape a distinct culture. Living long-term in low gravity, high radiation, and resource-limited conditions, residents will develop habits, thinking patterns, and values different from those on Earth. They may place greater emphasis on cooperation, frugality, and innovation, relying more on technology and collective intelligence to solve problems. The art, music, literature, and philosophy born on Mars will carry the marks of space exploration and frontier pioneering. Martians will have their own stories of home, they will be the first generations of children to leave the cradle of Earth, and their identity will transcend any single nation or ethnicity. Meanwhile, Martian society will face internal challenges. The scarcity of resources will make the fair distribution of food, water, and energy a core issue. They will need an effective political and legal framework to manage these resources and resolve internal conflicts. Environmental management, including maintaining ecological balance within bases and handling waste, will be a permanent task. Merging the diverse cultural backgrounds of early residents into a unified Martian community will also be a significant challenge. Yet, all these obstacles will serve as drivers for the further development of human civilization. Mars is not just a second home, it is a springboard for looking toward the deeper universe. The experience gained in construction, survival, and resource utilization on Mars will provide invaluable lessons for exploring other planets and moons, such as Europa at Jupiter or Titan at Saturn. Mars will be the first station for humanity to become an interstellar civilization. The final vision even includes the possibility of interstellar migration. Once humanity masters the ability to build self-sufficient civilizations on Mars and develops advanced spacecraft, traveling across light years to settle on habitable planets in other star systems will no longer be an unreachable dream. The successful colonization of Mars will prove that human civilization possesses infinite adaptability and creativity, heralding a vast future. The birth and development of Martian civilization will be a new chapter in human history. It is not just about technological progress but also about the growth of the human spirit, how we define ourselves, how we coexist with other planets, and how we ultimately transcend Earth to write our own legend in the vast universe. Mars is calling us, guiding us toward a more brilliant future. That concludes our knowledge sharing for today. I wish you all a wonderful dream and a beautiful day. See you next time.